Every particle in the universe follows rules, precise, mathematical, unbreakable rules. Drop an apple, it falls at 9.8 meters per second squared, every time, without exception. Light travels at 299,792,458 meters per second. Exactly that number, everywhere in the universe, always. The laws of physics don't vary, and here's the thing that keeps certain physicists up at night. That kind of perfect mathematical consistency is exactly what you'd expect if someone wrote the rules, not discovered them. Wrote them, coded them in, set the parameters, ran the program, and sat back to watch what happened. Because our universe doesn't just follow rules. It follows rules that look suspiciously like software. Let's start with Nick Bostrom. In 2003, a philosopher at Oxford published a paper that should have broken the internet before the internet was really breakable. The argument wasn't science fiction. It wasn't a thought experiment for fun. It was a logical trilemma, 3 possible futures, and he argued that at least one of them has to be true. Either virtually every advanced civilization goes extinct before it ever gets powerful enough to run realistic simulations, or every advanced civilization that does reach that point simply chooses not to run them, for reasons we can't fully imagine. Or we are almost certainly living inside a simulation right now. That's it, pick one. Because if even one civilization in the history of the universe ever reached the point of running detailed ancestor simulations, there would be vastly more simulated realities than real ones. And statistically, you'd probably be in one of the fake ones. Think about what that actually means. Right now, in this moment, you might be a pattern of information running inside a computational system that someone else built. Your memories, your sensations, the weight of the chair under you, the sound hitting your ears, all of it rendered, processed, delivered to a simulated consciousness that has no idea it's simulated. And the frustrating part is, there's no obvious way to tell the difference. A perfect simulation of reality would feel exactly like reality, because from the inside, it is your reality. Every sensation you've ever had came to you through the same interface. Your brain, which has always been your only window to the world. You've never actually touched the outside universe directly. You've only ever touched your own perception of it. Here's where quantum mechanics gets uncomfortable. Particles in the quantum world don't have definite properties until you measure them. An electron doesn't have a specific location. It exists in a superposition of possible locations. A smear of probability spread across space until something interacts with it and forces it to commit. Then it picks a spot. And this isn't just a limit of our measuring instruments. This is how the universe actually behaves. The particle genuinely doesn't have a fixed state until it's observed, which sounds insane, and it is. But it also sounds exactly like a rendering optimization. In a video game, you don't load the entire map at once. You load what the player is looking at. Everything else stays unrendered to save processing power. What if the universe is doing the same thing? What if quantum indeterminacy isn't a weird philosophical quirk, but a feature of a system that only computes the details it needs to compute? Then there's the speed of light. Nothing in the universe travels faster than 299,792,458 meters per second. Not almost nothing. Nothing. It's an absolute hard limit baked into the fabric of space-time. Einstein's equations demand it. Every experiment ever run has confirmed it. But why should there be a speed limit at all? In a physical universe with no underlying architecture, there's no obvious reason information or matter should have a ceiling. In a simulated universe, though, a speed limit makes perfect sense. It's the processing cap. The maximum rate at which the simulation can update. You've seen what happens when a computer simulation gets overloaded. It slows down, frames drop, time dilates, and here's the part that's hard to shake. Einstein's general relativity shows that time actually does slow down near massive objects, near black holes where gravitational forces are extreme and space-time is most severely warped. Time runs slower, which is exactly what you'd expect from a system under heavy computational load. The Planck length is the smallest meaningful unit of physical space. It's approximately 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 our equations break down. Reality itself seems to have a resolution limit, a point below which there is no finer detail. If you were designing a simulation and you wanted to save computing resources, you'd do exactly that. You'd set a minimum pixel size, a smallest unit of space below which no further detail gets rendered, because no observer can ever actually access it. The universe appears to have exactly that, a finite resolution, a smallest possible length. Scientists call it the Planck scale, and nobody has a fully satisfying physical explanation for why it exists. It's just there, built into the structure of everything. And then there's the fine-tuning problem. The fundamental constants of physics, the strength of gravity, the mass of the electron, the electromagnetic force, the cosmological constant, are all calibrated with extraordinary precision for life to exist. Tweak the strength of gravity by a tiny fraction, and stars never form. Shift the electromagnetic force slightly, and atoms can't hold together. Adjust the cosmological constant even a little, and the universe either collapses immediately or expands so fast no structure ever emerges. Astrophysicists have calculated that the odds of these constants landing where they did, purely by chance, are so small, they essentially don't exist. The universe looks, in the words of physicist Paul Davies, as though it knew we were coming, which is a strange thing for a mindless physical process to do, but it's exactly what you'd expect if somebody set the parameters deliberately. In 2023, physicist Melvin Vopson published research describing something he calls the second law of infodynamics. The core idea is that information in the universe behaves differently from everything else. While physical entropy increases, the entropy of information systems tends to decrease or stay constant. The universe seems to compress and optimize its own information over time, which is strange behavior for a random physical cosmos, but it's completely normal behavior for a computational system. Software optimizes. Simulations prune unnecessary data. If you were running a universe on a machine, you'd want it to manage its own informational overhead efficiently. And our universe appears to do exactly that, automatically, everywhere, all the time, as though it were written to. Neil deGrasse Tyson put the probability of simulation above 50%. MIT physicist Seth Lloyd has argued that the entire universe might be a quantum computer, processing information at every level of physical reality. These aren't people on the fringe of intellectual life. These are people who understand the physics. And the physics, taken seriously, keeps pointing in a direction that makes most scientists uncomfortable, because it's a direction that's very hard to test. And that's the real problem. The simulation hypothesis might be true, and we'd have essentially no way to prove it. Any evidence we could find would exist inside the simulation. Any instrument we could build would be made of simulated matter. Any measurement we could take would be processed by a simulated brain. The hypothesis is, in the most technically precise sense, unfalsifiable. You can't design an experiment that rules it out, because if someone built the simulation well enough, they could have built in any result you'd ever observe. That's philosophically unsatisfying. Science runs on falsifiability, on the principle that a real claim has to be disprovable in principle. A claim you can't even try to disprove lives in a strange no-man's land between science and philosophy, which is exactly where the simulation hypothesis keeps ending up. Some physicists reject it on those grounds entirely. Others point out that simulating a universe of this complexity would require more energy than anything we can imagine. Landauer's principle says that computing and erasing information has a minimum energy cost. Scale that up to every particle in the observable universe, every quantum event, every moment across 13.8 billion years, and the numbers become so enormous that even a Type 3 civilization commanding the energy of an entire galaxy would fall catastrophically short of what's needed. The simulation would require more resources than the universe itself contains, which is an awkward property for a simulation of the universe to have. Maybe that argument kills it. Maybe whoever built the simulation had access to something beyond our universe's resources. We genuinely don't know what's possible at that scale. There's also this. The simulation hypothesis doesn't actually tell us much, even if it's true. If we are in a simulation, the laws of physics still work exactly the way they work. Gravity still pulls. Light still travels at the same speed. Chemistry still follows the same rules. The experience of being alive is unchanged. The people you love are still real in every sense that matters to you. The simulation being real wouldn't make your life less real in any way you could feel. What it would change is the metaphysical furniture, the backstory, the origin of the rules, not the rules themselves, which some people find oddly comforting and other people find completely devastating, depending on how attached they are to the idea that the universe is made of something solid and unconstructed at its base. There's a version of the simulation argument that turns back on itself in a way that's genuinely hard to sit with. Researchers like David Wolpert have pointed out that mathematically, a simulated universe isn't necessarily less complex or less capable than the base reality running it, which means a simulated civilization could, in theory, run its own simulations. And those simulations could run simulations. And you get an infinite regress of nested realities with no obvious bottom floor. Not just us being simulated, but us potentially running simulations of civilizations who run simulations of us. All of it stacked and recursive and ultimately impossible to untangle from the inside. Wolpert's mathematics doesn't predict that will happen. It just shows it isn't ruled out by the physics or the logic. The floor you think you're standing on might be the ceiling of something else. Here's what's strange to sit with. Every major religion in human history has proposed that the universe was created intentionally, by something outside it, with purposes we don't fully understand according to rules that were set before we arrived. The simulation hypothesis is, on its surface, a secular version of that same structure. A creator, a designed reality, rules written in advance, and conscious beings inside it who can observe the rules but can't see the author. That parallel doesn't prove anything. It might just mean humans are wired to reach for that kind of framework when the universe gets too weird. Or it might mean something older than philosophy is leaking through. That the intuition that something made all of this is responding to real signals we don't fully know how to read. The physicist John Wheeler spent the last decades of his life developing what he called the participatory universe. The idea that consciousness doesn't just observe the universe, but in some fundamental sense participates in bringing it into being. That observation isn't passive, that at some deep quantum level, the universe requires minds to be real. He wasn't arguing for simulation. He was arguing for something stranger. That reality and observation are intertwined in a way we don't have the conceptual tools to fully describe yet. Whether that's a feature of a simulated system or just a feature of quantum mechanics or both, or neither, Wheeler couldn't say. He died in 2008 with that question open. It's still open. What we know right now is this. The universe follows mathematical rules with a precision that has no physical explanation. It has a speed limit that behaves like a processing cap. It has a resolution limit that behaves like a pixel floor. Its fundamental constants are calibrated as though they were set by something that wanted complexity to emerge. Its quantum behavior looks like a rendering optimization.